This 5-minute film is about the origin of life. But life is hard to define, so the film is really about the origin of microbes, primitive cells without a nucleus. 4.5 billion years ago, just after the Earth had formed, a Mars-sized planet collided with the Earth in what is called the moon-forming impact. This melted the entire crust and mantle. Massive amounts of magma were cast out into space, and from that material the moon was formed. As it concerns life's origin, the most important effect of the moon-forming impact was to convert the Earth into a blazing ball of magma, surrounded by vaporized rock. This boiled off all of the water that had come to Earth during accretion as steam into the atmosphere. All of the nitrogen from accretion was also expelled to the atmosphere, and importantly for origins, all of the carbon that had collected during accretion was converted by magma oceans to carbon dioxide that also went to the atmosphere. The surface of the Earth cooled rapidly, water in the atmosphere rained out, forming oceans that were twice as deep as today's, surrounded by an atmosphere of nitrogen and carbon dioxide, much like that of Venus. The last impactors made the surface a dangerous place to be, as any land environments were under constant attack. It was much safer at the bottom of the ocean, and this is where the chemistry relevant for origins was taking place. Most people know about black smokers, the hydrothermal vents that emit 400-degree hot water and that sit on top of submarine spreading zones. But there are other kinds of submarine hydrothermal vents situated far away from spreading zones. These off-ridge vents are less well known, but they are extremely relevant for life's origin because of their internal chemistry. If we take a cross-section, we can see that black smokers sit directly over a magma chamber. The water that circulates through them is superheated by close contact with 1200-degree hot magma. At off-ridge vents, the circulating water never sees magma and has a temperature of under 100 degrees. With these initial conditions, a process called serpentinization takes place that is essential for origins. Serpentinization generates chemical energy in the form of hydrogen gas. If we zoom in, we can see how hydrogen is produced. During serpentinization, the circulating water reacts with reduced iron minerals in the crust. They convert water into molecular hydrogen, shown here as white balls, while the oxygen in water molecules, shown here in red, remains in the crust as iron oxides. This hydrogen is the source of energy and electrons at origins. The hydrogen can react with the surface of metals and minerals that are produced in the hydrothermal vents. Hydrogen is chemically activated by the outer electrons called d electrons of the transition metals. On these surfaces, hydrogen meets carbon dioxide from the moon-forming impact, and the reaction of life is often running. The metals also activate carbon, oxygen, and nitrogen that can react with one another on the solid-phase catalytic surface. This is called heterogeneous catalysis. In the laboratory, such reactions generate amino acids and the most central compound in all of metabolism, pyruvate, an organic acid with 3 carbon atoms. Because these reactions release energy, there is nothing to stop them from going forward. Energy-releasing reactions are symbolized by flashes of light. Products can react further, and the backbone of microbial metabolism unfolds naturally along the lines of thermodynamics. Under the conditions of hydrothermal vents, 97% of all biosynthetic reactions in central microbial metabolism, starting from hydrogen and CO2, release energy. The further the compounds react, the more stable the products become. Stable products can accumulate on the surfaces of inorganic compartments, increasing their local concentrations and fostering polymerization. Products of organic synthesis can have their own catalytic activity. If products catalyze reactions that feed back into their own synthesis, autocatalytic networks can form. Autocatalytic networks promote molecular self-organization. They help bridge the gap between chemical reactions and living cells. Continuously fueled by the energy-releasing reaction of hydrogen and carbon dioxide, symbolized here by flashes of light, transitions to higher molecular complexity become thermodynamically possible. Small peptides and nucleic acids can accumulate and undergo their own molecular interactions. Nucleic acids generate a molecular memory, a currency of information that emerges from the metabolic network. This information is the basis of the genetic code, which directs the synthesis of specific peptides from RNA templates. This generates efficient catalysts and a rapid acceleration of molecular organization. But precursors must constantly be supplied, and the system remains dependent upon the reaction of hydrogen and carbon dioxide. Some compartments assemble enough information to incorporate inorganic catalysts into proteins encoded by genes. They can become free-living cells, but their thermodynamic drive remains dependent upon the reaction of hydrogen and carbon dioxide. The first bacteria and archaea in this theory were acetogens and methanogens, respectively, organisms that live from hydrogen and carbon dioxide and still inhabit the crust today.